Hey everyone, we are looking at the derivatives of e to the x, b to the x, and natural log x. And of course we will be co-starring with the chain rule because we are always using the chain rule. So let's start with e to the x. So on my calculator here I have my e to the x and then I have the end deriv. So let's take a look at the graphs. So here is, in its totally rapid speed, e to the x in blue. And incoming, in red, is the derivative of e to the x. And oh, wait, is there a mistake? It's on exactly in the same place. It's not a mistake. This is actually super cool. The derivative of e to the x is exactly equal to the value of e to the x at that point. So the slope at x equals 1 is e to the 1. The slope at x equals 2 is e to the second. How cool is that? This is the only function that does that. That's kind of fun and exciting. So that's our first rule. The derivative of e to the x is e to the x. Our second and third rules, I'm actually just going to give these to you. If you really want to know, go to pages 115 to 120 in the book if you really want to read where it all comes from. So basically though, like the b to the x, that's kind of actually e to the x is a special case of b to the x. Because b is just a number, so that could be a 3, it could be a 5, it could be anything. So like for e to the x, technically is the derivative would be using this same exact rule. If I replace the e with the b with an e, I would have e to the x natural log e, but the natural log of e is 1. So that's why it gets its own special rule. Plus it's just so cool that the derivative of e to the x is e to the x. It just makes me really happy. I don't know why. So as we're dealing with problems like this though, of course we have to deal with the chain rule. We know about the chain rule, right? You know, derivative of the outside function while keeping the inside function the same and then multiply by the derivative of the inside function. So the derivative of e to the cosine x, y prime will be, it's e to the, keep the inside the same, because our inside function is that cosine x. So there's the derivative of the outside is the e to the, while keeping the inside the same, that's the cosine x, and then multiply by the derivative of the inside function. So the derivative of cosine x, of course, is negative sine x. When you see something like just like a y equals 3 to the x, I just threw this in just so you could see it with a number instead of a variable. So it's just 3 to the x natural log 3. No big deal. So by the way, these three things, add them to the list. We always add things to the list. We love the list. The list will tell us in one page everything we want. Okay, looking at natural log of sine x. The derivative of natural log is 1 over the thing, okay? So our outside function is the natural log, our inside is that sine x, and remember, we're still using the chain rule. So natural log, we get 1 over, keep the inside the same, sine x, and then times derivative of the inside, so times the derivative of sine x, we get cosine x. Now if we want to get fancy here, if we multiply that, we have cosine x over sine x. Oh, that's just cotangent. That's kind of cool. It looks so fancy when we simplify. But do we have to simplify? No, totally don't. Okay. So you're less likely to see something like or y equals 3 to the x as you might see something like 3 to the x to the 5th. So let's take a look. Still chain rule. So y prime is, we have the derivative of the outside, so it's going to be the 3 to the, keep the inside the same, x to the 5th, natural log 3. That's our derivative of our outside function using this b to the x rule. And then times derivative of the inside function, so the derivative of x to the 5th, we get 5x to the 4th. Okay, let's take a look at natural log of x to the 5th. We're actually going to look at this twice, go figure. So if we take the derivative of this, we get 1 over x to the 5th, and then chain rule, so times derivative of the inside, we have 5x to the 4th. And cleaning that up, that 5x to the 4th over x to the 5th is really just 5 over x. Okay, the reason we're going to do this twice is, what if instead of using the chain rule, we use those log rules? And actually, with respect to dealing with exponents, log rules are your friend. So if I just rewrite this guy, instead of natural log of x to the 5th, if I rewrite that as y equals 5 natural log x, now I just have a dilation. So the derivative of it, y prime, is 5 times 1 over x, or 5 over x. That was a lot less work, wasn't it? Like, instead of having to chain rule the crud out of it, you can just use a log rule first, and then you didn't have to chain rule. It's kind of nice. Okay. If this problem showed up in our textbook, it would probably tell you to be clever. Let's just do it anyway. Let's just take the derivative. So 1 over, keep the inside the same, e to the x, but then times derivative of the inside. Derivative of the inside, derivative of e to the x is e to the x. Wait a second. Y prime equals 1? How is that possible? This weird thing is just y equals 1? Well, you know those log rules I just mentioned? Let's use them. If we use log rules, we get x times the natural log of e. But the natural log of e is 1. So we just have y equals x times 1, or y equals x. And so that means that when we derive that, y prime equals 1. So my point with these last two questions is that whether or not you use log rules, you still are going to come up with the same answer. Okay, one last piece. What if we need the second derivative of this guy right here? This 5 over x. What if you need to find y double prime? Probably looking at that going, well, I don't know. What can I do with 5 over x? This is what you can do, and please listen closely. Y prime, we can rewrite 5 over x as 5x to the negative 1. Good mathematicians turn new problems into old problems. We can derive this using our power rule, so that the second derivative, we get negative 5x to the, be careful subtracting 1, it's surprisingly difficult at times, negative 2. Do I need to rewrite that as negative 5 over x squared? No, I can leave it as it is. The key here, there's two keys. With finding a second derivative on this, one, you currently don't even know how to find the second derivative of something like 1 over x to the 5th times 5x to the 4th. That doesn't happen until the next chapter. Or even if we cleaned it up to the second step. Or even once we finally clean it up, we still have to be a little bit clever and go, oh, let's change this to an exponent. Let's make this new problem into an old one. So there are our derivatives of e to the x, b to the x, and natural log x. And again, add these to your list. And also, don't forget about the chain rule.